Hello there, I'm Alan Willison. It's my pleasure to welcome you to this meeting of the Hertford Astronomy Group. I'm absolutely delighted to see we've got some new people in the audience tonight, so wherever you heard of us, very special welcome to you. Please make sure you do have a word with either myself or other committee members before you disappear at the end of the day. We don't want you to think we're not a very friendly bunch. We really are. Just a few housekeeping things to begin with. The usual one is that we're not expecting to practice the fire alarm, so if it does go off, please exit via the exits each side, and if you would gather on the car park, and then we can check everybody is safe. Excuse me, toilets are just outside the door there, and if I could ask your mobile phones if you can make sure they're set to silent. I'm going to try and do that myself this time, although I can't guarantee any results on that one. For those of you on Zoom, it's lovely to see you here as well, and a very big welcome. And again, if you are a newcomer, a very special welcome to you. I do hope you can keep your hands away from the keyboards, especially the space bar, because that will activate the microphone. And although we will try to cut you off at this end, we don't know what may happen. We've got a slight change of the order of our programme compared to usual. We're going to have our main speaker, Robert, first of all, and then we're going to be followed by John, who will be giving us a talk about the night sky after that. That's to allow Robert a chance to catch a train back to Cambridge at a decent hour. So there will be a chance for questions. For those of you who are in the university, we will come round with a microphone so that everybody will be able to hear them. For those of you on Zoom, if you would submit any questions via the chat facility, we will read them out to the various speakers here. So, without any more from me, I'm going to pass you straight over to Robert. Robert, the floor is yours.
Thank you very much. So, you may find me wandering about a bit as we go through. Let me start by saying a little thing about the title before I move on to the next slide. That's a quotation from a very well-known book, really the first proper textbook on astrophysics, published in 1926, first edition, by Sir Arthur Eddington. Well, actually, I don't think he was Sir by that stage. Let's just say Arthur Eddington. And that is, you're doing. So that title is taken from his book towards the end, and here's the final quotation. Final sentence is, reasonable to hope that in a not too distant future we shall be competent to understand so simple a thing as a star. Well, he was perhaps a little optimistic in calling them simple. I will explain why he is right, but not entirely right, because we know an awful lot more than we used to. Right. So we understand the essentials now. That's what I'm going to start with. But there's an awful lot of details, and we don't really understand all the uncertainties there. And I'll try and be honest about what we understand and what we don't understand. So let's start with the absolute basics. What is a star? Well, of course, you all know what a star is. Really, it's our sun is our nearest star, and we believe that other stars are also round, spherical, like the sun. It appears spherical. Of course, all we see is a two-dimensional circular disk, but we also see that it's rotating, and so we can deduce that it's actually spherical. It's got a hot surface, but get a little under 6,000 Kelvin. And the power output from biological records has been constant for billions of years. So the power output is obviously something pretty powerful and long-lasting. Keep pressing the wrong button here. So, are other stars similar? Well, how do we know? Initially, of course, all we could see were points of light through a telescope, however large the telescopes. But you can still work out the surface temperature if you look at the colours of the star or the spectra. And we can then calculate the radius. We know how much is radiated per square centimetre by the particular temperature, and we just multiply fourth power of the radius. That's Stefan's law. The radiation is sigma t to the fourth, and then we can multiply that by the area of the star, 4 pi r squared, and then we can calculate the radius if we know the total luminosity. Now, total luminosity, of course, we can't measure directly. We need to know the distance of the star for that. Now, it turns out that although initially we couldn't do any better than that, by doing a bit of indirect imaging, using several telescopes and then combining the results, we can actually that allows us to estimate the size and even the shape directly. And that has been done. So, but basically, other stars are similar. I'm sure you're all familiar with the Hertz-Russell diagram, so I won't linger over that, but just to remark that 90% of all stars are on the main sequence, and then the giants, supergiants, and white dwarfs mark later evolutionary phases. We'll cover that. Well, I'm going to deal with model stars, but let's just say, first of all, that real stars may well be embedded in gas and or dust, which affects their appearance. They may be in a double or even a multiple star system. Many of them are. So they're in orbital motion, so they're moving around one another. They may be tidally distorted if the two stars are close enough together. And they can also be sort of attached or surrounding gas by magnetic field lines. And here is one example over here. Typically, they may be rotating rapidly, either as single stars or, as in this picture, this one is quite distorted, and that's tidal effects from the other star, but it's also rotating because it's probably tidally locked in the orbital motion. But we'll start with a very easy case. Isolated, no nearby gas, no magnetic field, no companion. And it's spherical, no rotation. So if it's not rotating, a sphere is actually the natural shape. If you take a given volume, it will naturally minimize its surface area, and that turns it into a sphere. Now, first question. Why does a star have a particular size? Well, that is because there is a balance of forces. There's gravity trying to make the star collapse, and there's pressure resisting that and pushing it outwards. So that's what determines the radius of a star. If you only had gravity, the star would just go on shrinking. And for the sun, that would take less than an hour. And if you had pressure alone, the star would simply disperse into space So the exact balance tells you what the radius is going to be. Now gravity is caused by the fact that the star has mass. What about the pressure? That's a bit more complicated. So let's have a short historical digression first. By about the mid-1800s, so getting on for 200 years ago, astronomers knew roughly the mass and the size of the sun, but they had no idea about other stars. Average density turned out to be about 1.5 times that of water, so that was rather curious. They couldn't think what it must be made of. But if it's denser than water, then surely it's a liquid. Because that's far too high for a gas, and it's obviously not solid. It's too hot for a solid anyway. So the first assumption was the stars were liquid. And some late 19th century models of stars, not real stars, but just gravitating masses, really, they were based on liquids. But then in 1907, the German Robert Emden published his famous book called, in English, Gas Spheres. And he explored gaseous spheres in which pressure balanced gravity and found that it worked. He could make models. But the pressure wasn't a realistic one. He just used a simple mathematical formula which related the pressure only to the density. Pressure going like some power of the density. So, are real stars made of gas? Well, yes and no, as you will see. What are they made of? Solid? Well, too hot, far too hot. Liquid? Still too hot, be evaporating. Gas? Well, it can't be that either because it's too dense. Gas particles are far too close together to move freely. The separation of the particles is of the order of the particle size. Whereas in a normal gas, the separation is very much larger than the particle size. So it doesn't leave very many alternatives, does it? Well, the answer is that it's what's called a plasma, sometimes referred to as the fourth state of matter. A plasma is an ionized gas. And that means that it's made of nuclei and electrons. And if you compare, if you have a neutral atom like this one over here, there's a nucleus there, and it's surrounded by a cloud of electrons. They're not really in orbits like that. And this is not to scale. The cloud of electrons is actually about 1,000 times the radius of that little nucleus in the center. So it's very much not to scale. So if the star is neutral gas, particle size, order atomic diameter, that's no good. But if the gas is ionized, the particle size then becomes of the order of the nuclear diameter, or the electron radius, which is even smaller. And so the separation now is enormously greater than the size of the particles. So the particles move freely, and the material, plasma, behaves like a normal gas, like the gas in this room. So the pressure has two contributions, however. It is gas pressure, really plasma pressure, but it's also radiation pressure. The gas is hot, and that in itself, and so it radiates, and the photons produce a pressure as well. For most stars, that's pretty well negligible. It's very small for the sun, certainly. But there are stars in which it matters. So the gas or plasma pressure, the nuclei and electron are so small compared to the particle separation that, in fact, this behaves like an ideal gas, and not like the gas in this room, which has complications in it. But that means that there's a very simple behavior of the pressure with density and temperature. In fact, the pressure is proportional to the density and also proportional to the temperature. Radiation pressure, as I say, the very energetic photons in a star's interior also exert a pressure. And that actually goes like the fourth power of the temperature. So very rapidly increases as the temperature increases. Right, so we already discussed the balance of forces. Force balance is between gravity inwards, pressure outwards. And for stars less than about 5 times the mass of the sun, that's the dominant source of pressure. Go to more massive stars, which have much hotter interiors, radiation pressure starts to become important. And in massive stars, up to 100 solar masses or more, which are very rare actually, radiation pressure may dominate. Force balance. Well, if you think about it carefully, the pressure is not uniform through the star, and because it's denser at the center, and the temperature is also higher in the center. So the central pressure is, in the case of the sun, 200,000 million atmospheres in the center. And at the surface, it's nothing like that. So there's obviously a change in pressure as you go inside the sun. It's a gradient. So the outward force is really that difference in pressure between the center and the surface. High pressure, by the way, also implies a very high density. Center of the sun is about 100 times that of water, and very high temperature as well, 15 million degrees at the center of the sun. And others, more massive stars, have even higher values. But despite those extreme conditions, the gas is actually simpler than the gas in this room. And certainly much simpler than the material of the Earth. Star is much, much more simple than the Earth. You can build simple models of stars, simple models of the Earth. They're all very complicated. So here is a model star. Warm surface, very hot center, an inward force due to gravity, outward force due to pressure. Balance determines the size. Next problem, why does a star shine? Well, you may say that's obvious, it's hot at the surface. But you have to think about what happens, because if it radiates away all the energy, it's going to get cold. And it will actually do that in about 10 million years. So there must be some energy source somewhere. You need a balance between the energy that's generated at the center and the energy that's radiated from the surface. And the central energy is generated by nuclear fusion, by hydrogen fusing together to form helium. And then, because the star's in force balance, the radiation works its way out and is radiated from the surface at the same rate as it's generated in the center. So we've got a balance again, energy balance between generation at the center and radiation from the surface. And so the star can stay stable for billions of years. And that requires energy, of course, to be transported somehow from the center to the surface. So energy transport plays a very crucial role in the structure of stars. And there are three, you've probably taught at school, there are three ways energy can be carried about, either by conduction, by radiation, or convection. And we recognize all these things in daily life. Conduction is caused by electrons moving along a metal rod, say, from the hot end to the cold end. So if you stick a poker in the fire, if you've still got a coal fire or a log fire, then of course the tip of the poker becomes very hot, and if it doesn't have a wooden handle, you're going to burn your hand sooner or later. So that's very common in solids. So we're very familiar with that phenomenon on the Earth. But it's actually not very important in most stars. There are some where it's critical. Then there's radiation. That's very common in stars. That's the emission of photons this time rather than electrons, but again going from hot to cold. And we're familiar with that if you have a radiator which is you're some distance from, you can feel the radiation, especially if it's of the old-fashioned type. And then there's convection. Now again, we're familiar with this. It's what happens when you boil water. You get convective motions in the water as it boils, and probably turbulent motions. So whereas the electrons and the photons, that's a microscopic property, convection is a large-scale property. These are motions on a significant scale, and in order to get them, they need to be in a region of steep temperature gradient. Boiling water in a saucepan, for example, it's hot, you're heating the bottom, but it goes, the energy is carried through the whole body of water by convection. So, conduction, as I said, is not very important for most stars. But stars like the Sun and less massive stars, radiation is what carries the energy in the interior, and convection carries the energy in the envelope around the interior. And the size of that envelope is larger the smaller the star. I mean, relative to the whole star. And once you get down to about 0.3 times the solar mass, 30% the solar mass, stars less than that are fully convective. Convection spreads inwards as you go down the range of mass. However, if stars are more than about 1.1 times the sun's mass, the convection shifts to the interior. There's a radiative outer envelope. So in that case, you don't have a convective outer layer, you have a convective interior, and the larger the mass of the star, the larger that interior. So the very largest stars will also have mostly convection carrying the energy, though there's always a thin radiative layer at the surface to allow the energy to radiate away. So, just to sum that up, in the more massive stars, whoops, wrong one. What am I doing? Come back. In these stars, you can see convection is in the interior, but radiation is in the outer bits. For lower mass stars, like the Sun, the convection is in the outer layer and the radiation in the middle. And for very low mass stars, it's all convective. So let's just remind ourselves of observed properties. Surface temperature is anything from 1,000 Kelvin, or maybe even less in some cases, up to 100,000 Kelvin or more. Remember, the Sun is about 6,000. The power output, or luminosity, is anything from a 10,000th of the Sun's luminosity to 1,000,000 times the Sun's luminosity. And the Sun is putting out 400 million billion watts. Now that's an incomprehensible quantity. But actually, it's quite interesting. I don't know whether that's, yes, it's a 1/5000th of a watt per kilogram. So it's actually not producing a lot per unit mass. And the human being, we produce a watt per kilogram, roughly speaking. So you are a far more generous radiator than the Sun, per unit mass. But of course, we're a bit smaller. So where does all that energy come from? Well, I'm going to digress here for a moment by talking about why Jupiter is shining. Part of that, of course, is reflected sunlight, but most of it is actually its own internal heat energy, which sounds odd. Jupiter is not a star, but it's a sort of failed star in a sense. It was formed by accretion that released gravitational energy, which heated the interior, and what it's doing now is gradually cooling down, very slowly, but measurably. So that was the first idea for explaining the Sun's energy, that it was just radiating away heat produced in the formation. But if you actually do this quantitatively, you can see that the Sun's output is far too high, because it will use all its gravitational energy up in only about 10 million years. And we know from geological evidence that it's billions of years old. So they need another energy source. And the energy source in stars, well, most stars, as I said, lie in the main sequence in the HR diagram, and all of them convert hydrogen to helium by a series of nuclear fusion reactions. Start with hydrogen, put 4 nuclei together, and you get helium. But you don't just get helium, you also get 2 positive electrons, 2 electron neutrinos, and some energy. Of course, the energy is the bit we're interested in here. And the Sun and all lower mass stars do this directly. This is so-called proton-proton chain reaction. But higher mass stars use catalysts. So you don't actually start with hydrogen, you start with carbon, I think it is, you start with, and start adding things. And you get carbon to nitrogen to oxygen, and then it goes back to carbon and releases a helium atom. But it's the same principle, and you get electrons and neutrinos as well. So, fusion reactions are very slow and stable, so that it can go a long time. And about 10% of a star typically is hot enough for fusion at the centre. So not the whole star, just a little bit of it where it's hot enough. And the lifetime is, crudely speaking, the amount of fuel divided by how fast you use it up. And fuel is the mass, and the luminosity is the rate of use. And for the Sun, that's about 10 billion years. And as you know, geology tells us that the Earth is about 4.5 billion years old. So we don't have to worry about the Sun running out in our lifetime. But of course, it's much shorter for more massive stars, because it turns out that the luminosity, especially for massive stars, depends very strongly on the mass. It goes like the mass to the 4th power. So that means that the lifetime goes like the inverse of the mass cubed. So it goes down rather sharply as you go up in mass. But anyway, at the end of the lifetime, whether it's 10 billion years for the Sun, or maybe short as 10 million years for some massive stars, all the available hydrogen is used up. So what happens next? Well, once you've used up all the hydrogen, what have you got left? You've got the products, the helium. So the central core of the star is now essentially made of helium. But the temperature is too low for helium to fuse. That requires much higher temperatures. So what does it do? Well, the only source of energy it's got at the moment is gravity. So the central core of the Sun, star, shrinks, and that releases gravitational energy, which keeps it going for a bit, but it also heats up the center. Half of it heats up the center, half of it is radiated, and not only that, it goes into expanding the outer envelope. So the core shrinks, and the outer envelope gets much bigger, by a factor of 100 or more. And the star becomes a... So in a red giant, you have a tiny core, which you can just about see there, and this huge outer envelope. And in fact, the contrast is much bigger than I was able to show it here. If I'd drawn the core at its appropriate size to scale, you wouldn't have been able to see it. It would have been a pinpoint. So, the shrinking core heats up, gets denser, until the temperature, instead of being 15 million degrees, is 100 million degrees Kelvin. And then helium can burn, or fuse. It produces carbon. A more complicated set of reactions, I'm not going to go into that. But once you've got helium fusing, you've got another source of energy that restores energy balance, and the core stops shrinking. And the star goes on burning helium in a stable configuration, but not for as long as the hydrogen burned. And eventually it also runs out, and you're left with a very small core which is made of carbon and oxygen. So what happens next? Well, that begins to get more complicated now. It depends on the total mass of the star. And for stars less massive than about 8 solar masses, the center never gets hot enough to burn carbon. And so it definitely has run out of fusion sources. And during the helium burning, it actually loses a lot of mass. Remember, it's a red giant now. You get stellar winds, takes a lot of mass off. And what happens eventually is that the outer envelope is completely ejected from the star, and you only have this carbon-oxygen core left, which is very hot, and that appears as a white dwarf star. And it rapidly makes its way down to a different part of the diagram. So here we have a white dwarf sitting at the centre of its expanding nebula. This is actually a planetary nebula. That's what they're called when they are at the stage immediately after the ejection of the envelope. Because the envelope drifts off into space, and eventually you just get the white dwarf left on its own. So what is the final fate of this white dwarf? Well, the interesting thing is that core, that white dwarf with a carbon-oxygen composition, it's supported against gravity as well, but it's a new kind of pressure, because the core is now so dense that quantum effects start to become important. And in fact, it arises, I'm not going to go into the details of that, by electrons undergoing various quantum interactions at very high densities. And so white dwarfs are actually quite stable. There's no energy support, any energy needed for this. This pressure is independent of temperature, so it just depends on the density. So the star can now cool without disturbing the force balance. And they cool very slowly, and my late colleague Leon Mestel did a lot of work on that in the 50s, and eventually it'll just fade into invisibility, which is a rather dull end. That's if it's a single star. More interesting things happen if it's got a companion, but I haven't really time to talk about that in detail today. So if they are in a double system, white dwarfs have a maximum mass, this is related to the quantum pressure, of about 1.4 solar masses. And if the companion star can transfer enough mass to it, the white dwarf may exceed that mass. Typically, a white dwarf has a mass of 0.6, 0.7 of a solar mass. So you've got to add quite a lot of mass to get it over this limit. But in that case, if it does go over the limit, it will explode as a supernova, like this one in here. I think you can just about see supernova there in M82, a regular galaxy. It then explodes, and in fact, often the white dwarf in the explosion is pressed inwards. It shrinks again and becomes a neutron star. Stars of more than 8 solar masses, in that case, the centre can become hot enough for carbon and, in fact, more massive elements to fuse. And the fusion will continue mostly by adding helium nuclei until the core is made of iron. And at that point, it becomes more difficult because iron is actually the most stable element that we know of. And so you gain energy by building up as far as iron. Beyond that, you have to put in energy to make the heavier elements. So here is the relevant curve. This is quite a complicated curve if you haven't seen it before, but this is the number of nucleons in the nucleus, and this is, well, don't worry about that. It just tells you how much you get out a given reaction. For example, going from hydrogen, whoops, I keep pressing the wrong button here, sorry, it'll come back, I hope. What have I done? I'll do. Yeah, so if you go from hydrogen down here up to helium, you're actually gaining something like 7 million electron volts, but that doesn't really probably mean very much. You gain even more. Oops, I didn't mean to do that. Pressing the wrong button here. So you gain much less energy going up. You gain a little bit every time till you get to iron, and then you will start losing energy if you make, or have to put energy in. But of course you can release energy from this end by fission, and that of course is the basis of atomic weapons, unfortunately. So what happens when it's all iron? The core is supported to some extent of densely packed electrons. And the densities are so extreme that some of the electrons actually get squeezed into nuclei. Now that means there's fewer particles around to provide the pressure, and the pressure drops. And that means the core can no longer support itself against gravity, and it collapses. And it bounces, because the core is a very rigid body. So the envelope can't penetrate it. It bounces out again, sends a shock wave out through the stars, and blows off the outer layers, and which are later seen as gaseous remnants. So here's a remnant of Kepler's supernova from 1605, and this is the 1987A supernova in the Large Magellanic Cloud. I was lucky enough to have some observing time just around the time it was coming down from maximum, and so I've actually seen this with the naked eye. So these are called core collapse supernovae, and they may also leave a core behind as well as this mass. And that's forced into collapse, and then if it's not more than 2 or 3 solar masses, the core may become a neutron star, supported now in the same sort of way as the white dwarf, but now by quantum pressure not of electrons but of neutrons, which behave very similarly to electrons in atomic terms. These cores are rapidly spinning. We had a physics teacher on one occasion, physics lecturer at university actually, who demonstrated the conservation of angular momentum by sitting on a stool and spinning, and then putting his arms out. And of course he slowed down. So what happens here is that it's collapsed, spins faster, and it may spin very fast, and may be seen, if they've got magnetic fields, they may be seen as pulsars. So this is an example of a calculation done to demonstrate this. Here's a more massive star in the sun rotating fairly sedately, becomes a red giant star with a carbon core. It has a supernova explosion, envelope is blown off, and the core shrinks, and it becomes a shell-like object with the expanding gas and now a neutron star which is spinning rapidly because of conservation of angular momentum. And because of relativistic effects, the light comes out in cones. And so it may or may not cross the path of the Earth. Right. If you have a really massive cores and they collapse, then it turns out that neutron stars also have a maximum mass. We don't know very exactly what it is, but it's of the order of 2 or 3 solar masses. And more massive cores than that, you can't form a neutron star, just keep on collapsing and very likely form a black hole. Where, as you know, I'm sure, gravity is so strong that not even light can escape. And these remnants, of course, are undetectable unless they happen to have a companion, in which case you can at least measure their mass. Or indeed, since 2015, they may emit gravitational waves, which we are now able to detect. But that's usually only if the stars in the binary system then merge. So, are stars really simple, as I claimed? Well, yes, in one sense. The structure is determined only by force balance and energy balance. And for most of their lives, stars have a very simple internal pressure, just pressure proportional to density and temperature. So the whole evolution can be understood qualitatively. But, of course, there are complications in detail, some of which I have indicated. Let me just talk about 1 or 2 of these. One of the most important things is that we are using standard physics, but we're extrapolating it beyond, much beyond, in most cases, the range which we can measure in the laboratory. So we're just having to hope that because laboratory experiments match all our existing theories, that the existing theories actually extend to the whole universe and all the different conditions that are there. Also, as I've mentioned, convection plays a major role in energy transport, but convection is turbulent. It's not just simple rolls like that, it's turbulent rolls. And you can observe this anytime if you look at a pan of boiling water. And that's not understood even in laboratory circumstances. So how do you describe convection? And the answer is you do it by introducing a parameter which you then fit to the observations. Not very satisfactory. And the other thing is, I've skated over this, but the ability of gas to transmit photons strongly affects the energy transport by radiation. But it's actually extremely hard to calculate or even to measure. There's a quantity called opacity, which is what you might expect. It measures the opaqueness of the material. And people have worked for years producing models which enable them to calculate that opacity, all based on standard atomic physics. But it's a very, very complicated calculation. I remember in the early 80s, there were 2 groups undertook this work, one in London and one somewhere in California. And they both came up with opacities. Fortunately, they did agree, more or less, but they weren't the same. And so, which is right? We don't know. And also, nuclear fusion is interesting because this is a case where you're actually dealing with energies which are much, much lower than you can measure in the laboratory. You can't do measurements of nuclear fusion at the rate that they happen in the stars. It happens at very low energies, and nuclear physicists simply can't measure these. So, are they really simple? Well, yes, but there are complications in detail. And we understand, nonetheless, stars, we understand them much better than Eddington did in the 1920s. So there's certainly been progress in the last 100 years. And our understanding is improving all the time. But it's also making stars more and more complicated, sadly. So we've come from Eddington, which is fairly simple, very readable book, by the way. It has a wonderful style. And then this was 400 pages. That was still quite a big book in those days. Recently, Echo Eben in the States couldn't do better than 2 volumes on 1,500 pages. Also a well-written book, but it goes through all the nasty bits which Eddington didn't know about. Right, I think that's it, folks. Yes.
Well, thank you very much indeed for a marvellously illuminating. To say that they're simple. Use this one. To say that stars are simple, well, it's very much an understatement, but you explained it in such wonderful detail that we can understand the simple bits and also understand the complexities that make it less so. So, I'm sure we must have some questions from the floor. So, who wants to go first of all? Thank you.
Do we know how long it takes for energy to radiate or convect from the centre of the star to the surface?
Yes, it's basically what's called the thermal timescale. So for the sun, it's about 10 million years. So for the energy to get from the centre of the sun to the surface is a long time.
How do we get, it sounds like a silly question, big stars? I'm thinking that if all the gas collapses into a star, eventually it gets to the point where fusion's going to start. Why does that not just blow off all the extra bits you need to make the star big? In other words, how does it get so big before igniting?
Well, it's a question of, that's a question about star formation, really. But essentially, a star starts from an initial gas cloud of a certain mass, and it will contract and produce a star of a certain mass. And it's become a star before any of the inside has become hot enough to burn. And by the time it gets to that sort of temperature, it's in pressure balance, and it's not going to get blown apart easily.
I think I follow that. Thank you.
And also the fusion reactions are really quite slow. Yeah.
Do we have any more questions? Are there any on Zoom?
Geff Briant has basically said the following. More of a comment or praise than a question. I was doing my degree at Sussex when you were there. I do have a vague memory of seeing you there. All I can say is that I wish the lectures I had were as good in explaining stellar dynamics and life cycles as you achieved tonight. A brilliant presentation. Well done. Sorry I wasn't there in person to congratulate you.
Oh,
That's Geff Briant.
That's very nice.
That was a lovely comment there. Thank you very much, Geoff, for that one. Do we have any more questions? Okay. Well, I'd obviously like to say a big thank you to you. I didn't give you much of an introduction at the start of the meeting, but to say that your journey from Glasgow down to Sussex and then your retirement. Now, I say that in inverted commas because those of us who retire know that you don't. And I'm really grateful that you haven't retired and that you took the time to come and visit us today. So thank you very much indeed. On behalf of the Hertford Astronomy Group, we'd like to say thank you to you.
Thank you very much. And thank you for the nice meal beforehand.
You're very welcome indeed. So have a safe journey. I'll leave you with our escort who will see you back safely to the railway station.
Actually, it's only 5 to 9, so I'm not rushing.
Okay. Well, feel free to stay if you wish to for a little bit more.
Stay a little bit longer.
Okay. Right. Do make yourself comfortable.
Yeah.
Right.
Just
Anyway.
wait a little bit. Right.
Is that a million or 1,000 million?
It's 1,000 million. Yes. Sorry. I'm afraid. Use is concerned.
Thank you very much. Okay, that takes us to the next part of our meeting, and John is going to come down and show us what we can look forward to in the next few weeks and possibly what people have been doing in the past few weeks. So over to you, John. Would you like this one?
I'm going to be juggling
here. I thought I'd start again with something for anyone who's learning the night sky, trying to work their way around the night sky. So this is the winter triangle. It's an asterism, and I don't think people should get too hung up about asterisms. Constellations are just asterisms that were invented thousands of years ago and given an official name to them. Any pattern you see in the sky is a valid pattern. You can draw whatever you want. We just have some we recognise. But this winter triangle I very much like because it's 3 of the brightest stars in the sky. You've got Sirius sitting down here. This is the brightest star in the sky. You see anything brighter up there, it's a planet, it's a satellite, it's a plane, it's a UFO. It's not a star. That comes in about -1.2. Procyon is about the 8th brightest star in the sky, and Betelgeuse over here, this is about, I think, the 10th brightest star in the sky. These two are only about 10, I think 8 light years away, and maybe 10 or 12, I can't remember. This is 500 light years away. This is a monster. Okay, but it's a lovely triangle. It rises earlier every night throughout the winter, and I used to like this because in the days when I was in gainful employment, I used to see this pattern in the sky rising earlier every night, all the way through the winter. And as it was coming, as it was setting, as I was coming home from work, I knew the winter was nearly over. There's quite a lot of stuff around here. I've picked out two Messier objects. You've got Messier 41, which is the little beehive cluster, which sits very low, just under Sirius. And about a third of the way up, you've got the heart-shaped cluster. Now, when Messier did his catalogue, he was using a telescope, I think it had about 3 times magnification. Now, admittedly, he had very dark skies. But anything he saw, you can probably see in a fairly low-powered telescope. And I always think globular clusters look fantastic in low-powered telescopes. So moving forward, what's ahead for the month? So it's going to be full moon in a couple of nights. It's going to work its way through to about the next meeting where we end up with the first quarter. Moonless night on the 1st of December. And we get 3 close encounters with planets towards the end of the month and the start of December. So Mercury, Venus, all right, I always start with the warning, standard warning, do not try to look at these when the sun is in the sky through any type of optical equipment. If you do, it's the sort of mistake you'll only ever make twice. Okay, Mercury's very low. I think you'd be lucky to see it. It's in the southwest, setting about 3:30, not long after the sun. It is about as far from the sun as it's going to get on this cycle. It starts heading back on about the 16th, so only 3 nights' time. It starts heading back towards the sun. It'll be coming around in the mornings. Venus over here, a bit better. You'll probably see this while the sun is still in the sky. It's -4 is incredibly bright magnitude. As I say, don't look at them when the sun's in the sky. So Mars is sitting in Cancer, fairly bright. You'll definitely be able to see it. It's quite distinctive red colour. Personally, I can never spot Cancer. I can never see these stars. But Leo is quite an easy shade to pick out, and Gemini is fairly good. Of course, you've got the brightest down there, and well, Taurus is off on the side, isn't it, of course. But this is worth seeing. About the 21st, we get a very nice conjunction between the Mars, the Moon, and the Beehive cluster. And I think, I keep meaning to try this, but I think with a camera, you won't even, reasonably good camera, but you won't need a telescope. You could get a nice image of the 3 of those, although I'm not sure how bright the Beehive cluster will be. Jupiter's spending its time between the horns of the bull over here. It will get close to the moon, about 4 degrees from the moon on the 17th. Uranus is hanging around near the Pleiades in the corner here. It's going to reach opposition on the 16th, so as you probably know, but in case you don't, that's when the sun, the Earth, and the planet form a straight line. And it's going to be the best time to see it. You'll get the best view you can of that planet at that point, so that's 3 nights. Saturn's sitting in Pisces. Right, Aquarius. I'm thinking they didn't look like Pisces. Saturn's sitting in Aquarius. It's actually coming out of retrograde motion. So as the Earth overtakes it, it starts heading the other direction. And I can never remember if it starts heading east or west now. I think it starts heading west, but if I'm wrong, forgive me. It's actually going to spend the next while chasing Neptune down. It will catch up with it in about February 2006. But it's going to be reasonably bright, and it'll be the brightest star, Saturn, in this region of the sky. So what happened last month? So we had the Europa Clipper got launched. This is NASA's flagship mission to Jupiter's moons. It's going to take it about 6 years to get there. I believe it's the largest satellite ever launched, or probe ever launched to the outer planets. It might be actually the largest one ever launched beyond the Earth. They had to use a full Falcon 9 Heavy and expend all of it to get it up there. It'll take it 6 years to get there. It will overtake the Icy Moons Explorer that European Space Agency sent up and get there a bit before it, and then it will spend several years orbiting. And I think it's part of its mission is to look for places to land on some of the moons on Europa. China released its roadmap for space science, and to say this is ambitious is really an understatement. This goes out to about 2050. There's a lot in it, which I very much skimmed the headlines. Most notably, they're talking about a manned mission to Mars in 2033, which seems incredibly soon, and a permanent base. They're going to double the size of the Tigon of their space station. They're going to put up a gravity wave detector in orbit. And I know ESA's planning to do this as well, but the Chinese are going to put one up. So it's really, really ambitious stuff. They're out to overtake NASA as the preeminent space agency, or the space power. I don't want to get into politics. I really don't want to get into politics. I'm not sure what's going to change with NASA with Trump back in power. He's very keen on getting stuff like moon landings and things like that. And he likes competing with the Chinese, so I don't know what's going to happen there. So Euclid was released, I think, last year, and it's mapping galaxies out to about 10 billion light years. And the idea of this is to form a map of dark energy and dark matter. Now, these are the biggest mysteries in cosmology. and this should give us a good handle on it. This covers about 1% of the sky that Euclid will cover, and it's going to be doing this for about the next 6 years, filling in the rest of it. I think this is going to produce some major scientific papers going forward, not just in dark matter and dark energy, but in an awful lot of cosmology. I think there's going to be a lot of stuff coming out of this mission. All right. So NASA has a new spacesuit for the Artemis astronauts. It looks like this. Now, it was actually designed by Axiom, who are the people, they do the inflatable modules for the space stations, where they where they can be compacted down smaller and expanded into a bigger volume. And they're talking about having tourist space stations. Prada worked on it as well. So Prada got most of the publicity, although I don't know how much they've got to do with it. I looked at some of the press releases and there was so much gumph in them. Something like redesigning the meaning of spacesuit development. But now it might just be me, but I remember NASA showing us some spacesuits for the Artemis astronauts a couple of years ago. I don't know if this is an extension of them or a replacement. I don't know what happened to that. Okay. China launched its 1,000 sails program. This is another satellite constellation. So we've had the Skylink one from SpaceX. We've got the one from Blue Origin, which is Jeff Bezos' one. This is the Chinese one. It's going to be about 1,300 satellites. I think there's at least 2 others in the pipeline. So low Earth orbit is going to get very, very crowded. Then we're going to have Kessler syndrome, and then it won't be a problem anymore. Okay. So, oh yes, Sagittarius A star. So I'm sure you remember this image here on the left, produced by the Event Horizon Telescope a few years ago. It's of Sagittarius A star, which is the black hole in the center of the galaxy. Now, some scientists at a Japanese university have actually disputed that this image is right. They're saying that these 3 stars and the dark part of the center is below the resolution limit of the telescope. A telescope that actually covers the entire Earth. It's below the resolution limit of the telescope. It gets very technical about optics, or the radio, whatever the radio equivalent of optics are. Event Horizon people have said, no, they made allowances for everything they pointed out, and it's definitely right. The Japanese scientists are saying it's actually far more sideways, I can't think of the word, because of that, sideways than this. This is fine. This is science. This is scientists publishing a result, other scientists examining it, kicking the tires, saying you might have a problem with this experiment, you might have this, we'll get better experiments or we'll get more exact work. This is great. This is science in action. Okay. Right, to my mind, this is the biggest thing that happened last week. We had a new section meeting. We had the very first meeting of the observation section. So it was about, unfortunately Fiona and I had tickets for the night they selected, so we couldn't go. I would have loved to have gone. Sorry? Yes, yeah, I had to book them very quickly. So apparently about 9 people turned out. It was a really good night. Saw a lot, and I think they were driven off about 10 or 11 o'clock by the Jew settling on equipment, but it was very, very good. I'd like to thank the guys at the back for organising this, because I think we've been missing this from the group for a while, and I'm really pleased. And I will really try to go to the next one. I would recommend it to anyone and everyone. I think if you're a beginner, it's great. If you're an expert, you can share your expertise, which is what the group's about. So speak to the 2 people at the back, and they will sign you up as soon as. Right, nearly done. I haven't gotten a lot of information for next month. So New Glenn was meant to, which is the Blue Origin super heavy lifter competitor to Starship from Jeff Bezos' company. That was supposed to launch about a month ago with a NASA mission, but they had to cancel it, or they postponed it till spring. I did see it was meant to launch early next month, within the next month, but I can't find anything that says it will, so I don't think it's going to happen. We've got a meteor shower at the moment. It's not a particularly good one. It peaks on the 18th, full moon's on the 15th. You know, sometimes like that. We may get another Starship launch. They have permission to launch from the 18th. They're going to try a few new things. What I've heard is they are going to change the heat shield, use a slightly different heat shield, and expose some other areas of the ship. They're going to come in, the upper stage is going to come in on a steeper trajectory, and they're going to try to relight the Raptor engines once it's in vacuum, which has never been done before. None of that sounds that spectacular. They may, although I've never seen anyone say this, they may try to land the upper section, which they haven't done yet. And we're due a good big blow up on the Starship, and they're always spectacular. Personally, I have doubts they're going to get this to work for 2026 when the human landing system for the Artemis 3 is supposed to be ready. I'm not sure they're going to risk a human being landing on the moon on this thing by then, but maybe. Okay, so the images. I've got to say, these are just the images that caught my eye. I could do easily 5 times as many. The quality of the images are just fantastic. These are the ones that caught my eye for various reasons. So this is, Stephen produced this one of the recent Aurora. I missed this one. And since then I put the Aurora app on my phone, so hopefully I won't miss another one. And I like this because you've got the Pleiades, I presume that is the Pleiades, yeah. The Pleiades, just lovely there, absolutely lovely. Different colours are different elements. I think the green is oxygen, but don't quote me on that. What I thought was funny was Stephen put this up and he said, who needs to go to Iceland? Guess where Fiona and I are going at the end of the month to see the Northern Lights. So thank you for that. Okay, Mikhail, this is a great one of Jupiter. I do not think that does it justice on the screen. It looks much better on my iPad. I think the light here washing out is a fantastic image. I don't think I've shown one of these before, and I think I'm going to be showing a lot of them. I did several of Jupiter, and they were all very, very good. Oh, yes. So a couple of months ago, I don't even remember, I showed a picture from Stephen of the Firework Galaxy, which is this just here. This galaxy's had about 10 supernovas in the last century. You normally, a galaxy that size, you'd expect one a century, hence the name, the Firework Galaxy. Over here, we've got a nice globular cluster, open globular cluster. And this is a dark nebula, an absorption nebula, known as the Seahorse Nebula. This thing's about 4,000 light years away. This is only about 1,200 light years away. I love the composition of this. I know they're actually very, very far apart, but it just shows you how crowded the sky can be if you know what you're doing. Absolutely fantastic picture. And, oh, sorry, I should have said this. This is where, officially, it's in Cepheus. But to me, it's right in the middle of Draco, Cepheus, and Cygnus. Okay, this one's from Peter. This is a planetary nebula, which we've all just been hearing about. This is a bipolar planetary nebula, which means we've got 2 lobes coming off. And as we learned today, this is the end of a star, well, not the end, the latest stages of a star that is old, about the same size as the Sun, up to 8 times, as the gas expands out. These do not last very long in astronomical terms. Apparently this one's about 150,000 years old, which is quite old for a planetary nebula, beautifully lit up. The star, or in the middle, is burning very hot now. And sending out X-rays. I don't know if that's why it's so bright still. Fantastic. Apparently, Peter's notes on this said it was only discovered, I think, about 12 years ago. And Peter does a lot. He does seems to be doing a lot of planetary nebulae, and absolutely fantastic pictures. They look like they're very technically difficult to do. This, I think he said it was 26 hours of exposure. And this again sits near Cygnus, just there. Okay, this one from Martin. This is the Crescent Nebula. Personally, I think this should be the Brain Nebula. It looks like you're looking down on a brain. This was, I believe, the gas was expanded when the star turned into a red giant. It became a Wolf-Rayet star, which are very, very hot stars, sent out more matter at much higher speed. And as it collides, it creates this amazing nebula. Absolutely fantastic. And I can't see my notes here. I haven't got my glasses on anyway. And I'm trying to remember how far away it was. You don't remember, Martin, do you?
It's about 7,000.
7,000 light years away. Okay. And I've got to say, I didn't pick these pictures out knowing they were all sitting around Cygnus, but this one again, these two bright stars take you down to Cygnus. This is about magnitude 1. I think that's magnitude 0, that's magnitude 1. They are fairly bright. Vega's quite bright and all. Can help you pick it out. I don't know if you guys will get together and all decide to take pictures of the same region of the sky, because I certainly didn't realise they were all in Cygnus, so close to Cygnus before I started taking the... of course, yes. Right. Okay, so that's it. I'm hoping there aren't many questions, or at least if there are, they're very easy ones. Okay, thank you.
Thank you very much indeed. A terrific presentation, wonderful pictures, terrific work gone on behind them. Do we have any questions for John? Gosh, you're very shy. Yeah, Richard was almost going to. He's chickened out a bit. Anyone on Zoom, any questions for John?
Sorry, can you repeat why they're all in Cygnus?
Because it's on the zenith. It's easier to look up and see a star. You look through less atmosphere, so it's easier to take pictures of. I'm guessing I've taken about three astrophotographs in my life, and you said they're all in the Milky Way. But was that significant?
Yeah, it's a lot of stuff. A lot of nebulae.
All right, it's a crowded area.
Any more questions? Okay, right. Well, I'd obviously like to say thank you very much indeed, John, putting such a great presentation together and showing us what's been going on, and also what's been going on with you as members of the club, which is brilliant. I've got a few other announcements, not very many, but just some dates for your diaries. First of all, in 2 weeks' time here, we've got the HAGAS, the astrophotography group, a meeting, and they've got a talk by Daniel Sundstrom. Pardon me if I pronounced that incorrectly, but it's a talk on astrophotography live from Sweden, and it's being on Zoom. So if you want to come along to that, you're very welcome to. So that's 2 weeks today in this building. It's one of the rooms upstairs. Our next Bayfordbury meeting is on the 6th of December. So again, if you want to come along, either if you want to come as a visitor, that's fine, you can book your tickets. However, if you want to come along and represent the club, you can bring a telescope along, let people look through it. Even though it was cloudy, we managed to see Saturn and Jupiter last week. They might have been fake ones, but I can tell you the people who looked at them were absolutely amazed, thrilled and delighted about it. So well done again to Richard for having produced these fake planets, and it did give people something to look at and something to talk to us about, which I think was one of the most important bits. If you're not so inclined to stand outside shivering, we do also have an indoor stand where you can talk to people about astronomy. We have the virtual reality set up, all sorts of reasons for you to be there. And of course, if you're representing the club, you get in free. And that's worth it, because you can wander off for an hour or so and have a little look around as well. That's on the 6th of December. Our next meeting here is on the 11th of December, when we've got the governance of the final frontier. So the final frontier, those words mean something to me, and we'll be giving prizes for anybody who dresses up in suitable attire, and that also goes for you on Zoom as well. If you want to dress up as your favourite Star Trek character, you can give us all a laugh as well. But for those of you who come to the university, we've got a little extra for you because it's coming up to Christmas. We will be starting the meeting a little bit earlier, 7:45 or so, with a mince pie and some mulled wine, just something to get us in a little bit of the festive mood. So do come along to that. Other than that, I'd like to say a very special thank you, especially to Steve, because we've been a person down today, and Steve has managed brilliantly there to get all the electronics going. I'd also like to say thank you. I'd like to say thank you to all the rest of the committee as well, who've pulled together to make things happen. We really do work well as a team, and your support and encouragement only makes us feel good about it. So until the next meeting, do have a safe journey home, and we look forward to seeing you again. Thank you and good night.